Hello again. Let's look at this particular example of implicit differentiation, and we're going to use that to find dy by dx. So consider this equation right here, radical xy, everything inside, and then that equals 3x minus 4y squared. So now let's get started. So now this equation implies, and let me get my grammar at least tolerable. I guess I should capitalize. So this equation implies that dy by dx of radical xy, if this equals that, then the derivative of this certainly equals the derivative of that. That's all I'm saying there. Okay, and that implies that now it's more handy with the square root of the product of xy is the square root of x times the square root of y. We're assuming x and y are positive, of course. But anyway, we're going to write that as x to the half, y to the half. And then remember, the derivative of the difference is the difference of the derivatives of the pieces. So we just do d by dx of 3x minus d by dx of 4y squared. And it is true, y is a foreign variable. And it does, in general anyway, depend on x. So what do we got to do, guys? So let's see. Let's go down. Now, by the product rule, I do one and leave the other alone. And then plus I do the other and leave the original one alone. So I derivate the x, let's just derivate the x term first, let's just say. The half, remember by the power rule, the half comes down and we get negative half up here. Now, and we leave y to the half alone, from the product rule. And then plus, now it's time to do the y, operate on the y term. The 1/2 comes down, again, now this time we get negative 1/2 up there with the y term. But since y is a foreign variable, and since we're differentiating with respect to x and not y, we have to put dy by dx. If we was doing derivative with respect to y, we'd just have this guy right here, and that'd be all. Just the half, this x to the half and this y to the negative half. But because we're differentiating with respect to x, I have to stick in this extra dy by dx. Okay. And then over here, d by dx of 3x is just 3. X is the native variable. Now, d by dx of 4y squared, I still do the power rule. I get 8y, but then I have to do the dy by dx. And guys, so you have that. And then the trick is, after that, get your dy by dx terms on one side of the equation and your terms that don't have it on the other. That's the main idea. And just this next step is more elegance than it is necessity. I multiply both sides by -1. So that minus 3 is now 3 minus that. And then these two negatives turn into positives. This is you can see the direct positive here, and this is an understood positive 8 here. And when I say positive, I don't necessarily mean the overall term is positive. I just mean the coefficients are positive. The 8's positive and the 1/2 is positive. They used to be negative up here. So I distributed -1 through this guy that was up here, and I got this guy here, and I distributed -1 through this guy to get this guy. Okay. And then, now the next thing we're going to do is factor out dy by dx right here. Now you could just as well put it over here on the left side of the bracket, either way. But anyway. And then we're just going to divide by everything in this expression that's in the brackets here. So we divide both sides by the 8y plus this guy here. And so we're just going to get this, so we divide both sides. And so this 3 minus 1/2 x neg half y half stays up here, and we divided it by this guy over here to get the dy by dx by himself. Now, your professor, he or she, they really might want you to get rid of the 1/2 and the negative exponents, and we'll do that. That 1/2 suggests to multiply by 2. The negative half powers suggest to multiply by x to a positive half and y to a positive half. So what we're gonna do is, by algebra, I'm gonna multiply top and bottom by 2 times the square root of x times the square root of y. Okay. And what's going to happen is that when we distribute, these x to the positive halves are going to hit those x to the negative halves and fizzle off. And of course, the positive half, if the positive half bumps into another positive half, we just get a 1 in the exponent, and we're happy anyway. Okay. So let's see. Let's keep this guy in view up here. So distribute 2 radical, 2, and when I say radical, I guess I need to be careful. I mean square root. So 2 square root x square root y. Distribute that through. Multiply it by 3, you just get 6 times square root x square root y. Now here's the fun part, minus. That 2 and 1/2 kill each other. That's good. That's what we wanted it. That's what we wanted it to do. That x to the half and x to the negative half kill each other. They're gone. And when I say they kill each other, they multiply to 1. Because remember, in multiplication, 1's the identity and it doesn't affect anything. So 2 and the negative sign's here, but the 2 and 1/2 multiply to 1. And then the x to the positive half and x to the negative half multiply to 1. Now the y to the pos half times y to another positive half, that's y to the 1 power, which is just y itself. The 1's in the exponent, but that's easy. That's just y. Okay. And then over, and we do a similar thing down here. The 2 times 8's 16. The x to the half has nobody to go with, so he just comes down as is. Now the y to the half bumps into y to the 1, and remember by the law of exponents, 1/2 plus 2 halves is 3 halves. Now here's the fun part, plus, now the 2 and 1/2 just kill each other off to 1. The x to the 1/2 and x to the 1/2, that gives you x itself. And then y to the 1/2 times y to the negative half just cancels off to 1. It's gone. So there's that, and we're done. Now guys, I think at this point, most professors would be more than happy if you stopped here. Okay, I think that should be good. But if your professor is a little persnickety, he or she has the right to be that way. And they don't want radicals in the bottom either. Well, you'd have to multiply by the conjugate of the denominator, and by conjugate, that may be a bad word, a sloppy word. You just you multiply by, imagine replacing this, don't really do it yet, but imagine replacing this plus sign with a minus. Now you got to keep this original term here. You can't just get rid of this term with the plus here. But you stick the same term here, except it's got a minus sign, instead of a plus sign here. Now, it's not the same term. This is the conjugate of this. These are not the same term at all, unless there be any mistake. But they have a certain look-alike about them, even though they're not totally alike. After all, you have a minus sign here and a plus sign here. That's what the difference is. So, but notice that this was not native. We stuck this in, we stuck this multiplier in down here, so you got to plug it in up here as well. If you multiply the bottom by some number, you got to multiply the top by that same number. Okay. We want to keep the same overall fraction, obviously. Okay. It'd be cheating if we didn't. We'd be wrong. Okay. So, but we're good to go. So there's that and there's that. Now the whole point of doing this is to get difference of squares down here. Like remember, a plus b times a minus b is a squared minus b squared. I'm letting my a be the 16 x half y 3 halves, and I'm letting my b just be plain x. So a squared minus b squared. But what's going to happen is when we square this, those fractional powers are going to go bye-bye. And so we're going to get, excuse me there, guys. So we're going to get 256. And remember law of exponents, 1/2 times 2 is 1, so x to the 1 power, which is x itself. And then 3/2 times 2 is 3, so y to the 3 power. And then minus x squared is rather boring. That's just x squared, and that's it. And what I did up here in the numerator, I factored xy off of the first term and the last term, and that gave me 96y plus 1 times the xy. And then I filtered a -4 and a radical xy out of these two middles, and that gives you positive 3x plus 8y squared. But guys, I would just, if I were you, let's just, there's no point in doing this unless you just want to. This is kind of silly to me. So let's just stay with, so what that means is, we didn't do anything wrong, but we kind of wasted our time in the numerator. It's better just to leave the numerator like it is right here, okay? So let me do a copy and paste, which is always a little dangerous. But if I do a copy and paste, well, I don't think it did the copy and paste. So let me do a copy and paste if it will so allow. Okay. And what I'm going to do is I'm just going to go ahead and do my squaring here that I did a minute ago. Well, I have to get rid of it. So that 16, remember it squared, if you square 16, you get 256. If you square x to the half, you get x. If you square y to the 3 halves, you get, well, y to the 3 by the law of exponents. Now the 16, you just have to brute force square it. 16 times 16 is 256. So, but that's all, guys, for that one. And let me hit that. And I really should put my implies there. And let me just put stop here. Or if you insist. Because this numerator here we didn't really get anything done by doing this. We didn't do anything wrong, we just didn't get anything accomplished. So let's just stop here. And let me just put final answer. Alright, that's good. And I'll save that, of course. But anyway, there's that. Now let's look at the next example. I'd like to make the most of the video, I guess. Get down there. Okay. Sorry, I was talking to my computer screen. I don't know why I do that. Okay. Moving on to the next problem. The sine of x plus y equals 1/5. Now that implies, guys, if that's true, well, if I do the derivative of both sides, okay? If the sine of x plus y is 1/5, well, let's see. What do I get here? Let me stick d by dx on both sides. Now, here's the deal. If the sine of x plus y equals 1/5, then I get either the why do we say this? Either the cosine. Now the cosine could be 0. Wait, that's impossible. So forget that. By the law, remember, sine squared plus cosine squared equals 1. But here, if we did it that way, sine squared plus cosine squared would equal, well, 1 over 25. Like if you square 1/5, you get 1 over 25. If you square 0, you get 0. And if we added the sum of those squares, we'd get the 1 over 25 because, 1/5 squares to 1 over 25. 0 squared is 0. 1 over 25 plus 0 is 1 over 25. But that can't be because, guys, if the sine of something is 1/5, the cosine would have to be whatever it would have to be one of the two numbers that it would take to. It would have to be a number that would give me such that sine squared plus cosine squared is 1. So this is impossible. Okay, so that was bad pedagogy on my part, and I'm sorry about that. So let's not even worry about that. Let's just go ahead and do implicit differentiation. And let's forget about all that. Okay, the cosine is not going to be 0. Bad things would happen if it was, but it's not. Okay, so if I do d by dx of both sides, now guys, remember, you just get 0 over here because d by dx of 1/5 is just 0. I've got to do d by du of sine u times d by dx of my u term, and I'm letting u equal x plus y. I guess I should scroll down. My u term is going to be x plus y, and I should define it down here at the very end. Oops, I need to do that. I forgot to do that. So suffice it to say my u term is x plus y. That needs to be defined. Always define your terms, right? Now, which implies that the cosine of u, now if d by du of sine u is cos u, or cosine u I should say, and then d by dx of x plus y, well, d by dx of x is 1, d by dx of y is just trivially dy by dx, okay? So there's that, and all that equals 0 from before. And let me get rid of that. That's stupid. It's true, but I don't need it. Well, yeah. Let's see. So there's that. And now cosine of u is not going to vanish, right? So now we replace u back with x plus y. And so we get the cosine of x plus y times this equals 0. Okay. And you know what? I do need that and statement because it's true. We already know from the sine equaling 1/5 that the cosine cannot be 0 because sine squared plus cosine squared is 1 from trigonometry. Okay. So we get, now this implies that this is true, and that implies, and let me just go ahead, well, let me just go ahead and put that stipulation back in there. Yeah, I don't want to be too perfectionistic, but I better put that stipulation back in there. Cosine of u is not 0. Okay, and I'd like to have all my stuff on the same line here, so let me arrange that, please. So let me see if it will be nice to me. Come on, there we go. Okay, and that's going to imply that this naturally, now again, guys, d by du of sine u is cosine u, d by dx of this is just this. Now we need that extra stipulation though, and the cosine of u does not vanish. And I need that stipulation up here, so that, and I need to put implies, and I need to stipulate here, and the cosine of x plus y, since we didn't define u on this second line here. Oops. Nope. Sorry. Not equal to 0. Okay. So the sine equaling 1/5, that implies that d by dx of this equals d by dx of that, but it also implies that the cosine by trig, this cosine is not 0. Okay, by trig. Oh, well, I wish I'd keep everything on the same line, but I don't guess it's going to. But anyway, you get the idea. By trig, this is true. By calculus and common sense, this is true. And by this guy up here. If this guy up here weren't true, this guy down here wouldn't generally be true. Okay, to say the least. Okay, now, so again... So sine x plus y equals 1/5. So we derivate both sides, and we note that the cosine doesn't vanish. We replace x plus y with u, and then we do the differentiating, and then we plug x plus y back in for u here. Okay, and then also for here, for the trig condition of cosine not vanishing for this particular problem. And now let's see, which implies... Now, guys, since the cosine doesn't vanish, now here's where you got to be. Here's why we needed that stipulation, that trigonometric stipulation. Now, there are other situations where cosine can be 0, but not in this problem. So, since the cosine of x plus y is not 0, the only thing, we have no choice but to conclude that 1 plus dy by dx equals 0. Okay, we can safely conclude that. Otherwise, we wouldn't be safe. You know, for all we know, this guy could be the 0 guy, or they could. They might could, take turns being 0. But no, by continuity, I don't necessarily think that would happen. Let's not get into that. But point is, cosine of x plus y will never be 0. So, this must always be 0. Okay? So, now guys, remember, x plus y, they're not completely arbitrary. X and y have to be such that x plus y is a number whose sine equals 1/5. Again, x and y are numbers such that the sine of their sum equals 1/5. They're pretty restrained. Okay, so, and with that restraint in place, we was able to get 1 plus dy by dx equals 0. Now that implies, just subtract 1 from both sides, dy by dx equals -1. Okay. And you know what? If dy by dx equals -1, there's it turns out that it actually turns out later when we do the antiderivative, you can kind of tell it's true now. This actually implies that y equals -x plus c for some real number c. But this is actually overkill. All we were asked to find was dy by dx, and we've done that. It equals -1. But if they ask you, let's say that your professor really gets persnickety and not only wants dy by dx, but wants y itself, well, later on when we do the antiderivative, you'll get y equals -x plus c. And this is a negative sign right here, guys. And let me tap that in the palette where it's more visible. I'm running out of time, so I'll have to hurry. So let me type that in real quick. Y equals -x plus c. And that's good. So y equals -x plus c. Because after all, if you did dy by dx of both sides, you'd have dy by dx equals -1 because the plus c would just get killed. It's a constant. Constants just get killed with the derivative. Okay, x and y are variables, but c is a constant. Okay, so we found our dy by dx, and later I'll show you how to find y. I've not really showed you the antiderivative yet. Don't worry about this part just yet, okay? Just worry about the dy by dx part. Guys, that'll be all for this video. I'll see you on the next video. Bye-bye.